So I'm Claudia Muni. I've come from University College London, where I'm doing my PhD with Professor Andrew Ponson and Dr. Jason Sanders. Here's also a list of other people I collaborate with and who have been to various degrees involved in the work I'm going to talk to you about today. So today I will tell you how we can make dark matter density profiles more precise using dynamical information. So first, I'll give you a quick recap. So today we think that most galaxies are embedded within dark matter halos, and that this dark matter halo extends much further out in radius than the galaxy at the center. And we think that the dark matter within the halos is not distributed evenly, but the halo is densest near the center, and then the density decays as you go further out in radius. So by measuring the density of dark matter in radial shells from the center, we can construct our dark matter density profiles. So kind of like this one here, where every point is a radial shell around the center. And these density profiles are very important. We especially care about the inner regions, which is kind of like the shaded area here. And this is because the exact shape of dark matter halo profiles contains a lot of information about the nature of dark matter. For example, we think that our model of dark matter will change the shape of the profile, whether the dark matter particles are heavier or lighter, or the type of interaction between the dark matter particles we think will affect the shape of the density profile. So that's why we want to make our profiles as precise as they can be, also because they're extremely important when we do our calculations for example, indirect detection experiments. So we want to make our estimates of these density profiles more and more precise. And usually we infer our density profiles from observations of halos, but then those observations need to be compared to theoretical predictions. And those theoretical predictions are based on running numerical simulations of dark matter halos. And when we do run our numerical simulations, what we see usually from running cold dark matter only simulations, so without baryons, we see that the profiles can often be described quite well by power laws. So you've heard of the NFW or the INASTO profiles. And these profiles, the power law ones, are quite good at approximating the shape of the profile for most of the radial extent. But then they kind of struggle at small radii and a larger radii, so at the virial radius and beyond that. So here in this graph, for example, the red line would be a density profile, and the yellow lines are the NFW and INASTO profiles, the power law ones, and they kind of struggle to represent the profile in those regions. And the small regions are the ones we care about most because they can reveal so much information about the nature of dark matter. But even from simulations, it's very difficult to probe those inner regions because, first of all, statistical fluctuation of Poisson noise. So we have very few particles, a small radii. So your noise will be very high, and that can hide the true shape of the density profile. And then there's also other related problem, like the finite resolution of our simulation. So whenever you have your resolution, you have a finite effective size of your particles, and that's limiting your resolution in those inner regions. And a way around that is just to add more particles, but that adds computational costs. And then about the outer regions, well, those are they're not very well represented by the power law profiles because of the contribution of particles that live in the outskirts of halos, and those bring in out of equilibrium effects, and then they alter the density profiles at the virial radius and beyond. So we need better representations of the profiles, especially in those two regions, to better understand what's going on with our dark matter profiles. So what we did was use a dynamic space method that we call dynamical density profiles. And the idea behind this method is that we take the particles from our simulation, which are just points, and we transform them into orbits. So in practice, we are smearing the particles along their orbits, so they now cover the entire space of their orbits. And by doing that, now the particles will spread across multiple of those density bins, so they will cover multiple radial shells, and that will bring the statistical noise down because the particles are extended into orbits. So how is this method different from what has been done until now? So the traditional, what we call binned profiles. Well, the binned profiles usually are based only on taking the position of the particles. And so you take a snapshot in time from your simulation, so a frozen instant of the simulation, and then you divide up your space into radial shell, starting from the center. And then you add up the mass of the particles within each shell. You divide by the volume and you get your density per shell. But this method is really throwing away half of the information about the phase space of the particles that we have from our snapshots. So that could be missing some important information that we could include in our density profiles. So what we do instead is include that dynamical information, and that's why we're calling our profiles dynamical. So how do we construct these dynamical profiles? First of all, we calculate a spherical gravitational potential, and then we want to find the orbits of the particles so we can smear those point particles along their orbits. And here I wrote we integrate the orbits, but in practice, integration is a very slow method. And doing that for hundreds of thousands or millions of particles is very difficult, computationally expensive. So instead, what we do is calculate a probability density of where you would find your particles. So this graph here is represents the probability of where you would find your one of your example particles, a different radii, and the higher the probability means the more likely you are to find your particle there. And this is for an example particle, which would have a pericenter about 4 kiloparsec and an epicenter about 9. And we do this for each one of the particles in our snapshot. And then in order to find the dynamical density, we add up all the probabilities and then we multiply by the mass, divide by the volume, and you get a first estimate of your dynamical profiles. So once we have a first estimate of our dynamical profile, we're not quite done yet. And that is because once we spread the particles over their orbits and we spread them over multiple density bins, then what we generate is a new mass distribution, which is inconsistent with the original mass distribution that you have from the original snapshot from your simulation. And this is because the particles are now spread out as opposite to what they used to be in the original snapshot. And that means they cover a different amount of space. And so the mass is sort of redistributed, and that is inconsistent with the original simulation. So a way around that is that we iterate our profiles until we obtain a consistent potential density pair. So what this means in practice, to understand this a bit more, I made this flowchart. So this is our entire method. So we start from our snapshot, which is direct from the simulation. Then we find the mass distribution and potential within from the original snapshot. And then we calculate the particle orbits within the potential given by the snapshot. And then we have our first estimate of the dynamical density profile. Once we have that, then this dynamical density implies a different mass distribution from the snapshot. So we need to find the new mass distribution and the new potential, then calculate the new orbits for the particle and kind of repeat this loop a few times until we reach convergence in the density profile. So we applied this method to a selection of 7 snapshots, which come from different simulations with a wide range of masses. So going from 10 to the 9 solar masses to 10 to the 12 solar masses. And another thing we did is to resimulate each of our simulation is resimulated both at a low and a high resolution simulation. So we have a lower resolution simulation and a higher resolution one. And the reason why we did this is because we want to apply our method to the low resolution version of the snapshot and see how it compares to the traditional, to the binned versions of the density profiles for both the low and the high resolution simulations. So I'm going to show you an example here of one of the results we obtained. And this is just one of the halos we looked at, but this is kind of summing up all the main results that we see across all halos. So if you focus on the orange points here, those are the traditional estimates for the low resolution snapshot. And then the black dots that you can kind of see here are the bend estimate for the high resolution simulation. And then the blue line that you see here, that is our dynamical estimate. And the dynamical estimate that we have comes from only from the low resolution version of the simulation. So it knows nothing about any of the high resolution profiles. So what we see straight away here is that our dynamical profile agrees well with both our bin distribution for most of the radial extent anyway. I'll say a few words about beyond the virial radius after. And then what is maybe harder to see here, but maybe will become clear later, is that the Poisson noise is also considerably reduced with our method, especially in the inner regions that we care about most. So as I said, we apply this to all of our halos, and the results are consistent for all of them. There are some small differences for some of them, and I don't have time to go into why now. But if you're interested, we can chat later, or you can ask. I'm happy to talk about it. But the main results that we saw for our example halos are true for across all of our halos. So let's go back to our example now, and we can focus a bit more on the inner regions. So this is just a zoom of the inner regions of the example halo. And what we see straight away here is that our density estimate, so the blue line, which is at the same resolution as this red point, extends further in radius compared to our estimate, to the bend estimate, the traditional bend estimate. And this is because we tend not to trust our bend profile below some radius of convergence, which I've marked here with this arrow. And that's because your errors there, your Poisson noise becomes high, and also because of relaxation effects become important there. So there's no convergence below this radius. But instead, with our profile, now we can take some of the orbits that come into small regions. So the profiles can come from particles that normally would live in a larger radii in our simulation, in our snapshot. And those come in and they contribute to bring down the noise at small radii. So that's why we can extend our profile further in. And then we can compare it to another interesting result that we see is that we can compare it to the bend high resolution. And we see that our dynamical estimate, even though it doesn't know anything about the high res, is sort of following the same trend that is set by the higher resolution simulation, which is a very interesting result and very promising. It cannot eliminate every single difference with the high resolution simulation, and I can go into that later or you can ask me about it if you're interested. But it's definitely a promising result and a step in the right direction. So we repeated this. We applied our method again this time to the high resolution simulation, and we made another simulation which we call ultra high, which is even higher than the high resolution simulation. And this is marked here by the pink dots, that's the ultra high. And now the blue line and the black dots are at the same resolution. So we apply our dynamical code to the high resolution simulation. And I'm just showing the low res here for reference. And this is just to show here that the results that we recover from the low resolution seem to agree in the case of the high res as well. So when we're comparing the high res to the ultra high res, the dynamical profile seems to show the same properties that we saw for the low res. And this is just to show that our method seems to be resolution independent. So it doesn't matter what the original resolution of your simulation is, this method should return the same results anyway. And finally, I'll say a few words about the outer regions. I don't have too much time to go into this, but it's very interesting results, I think. So feel free to ask me or come and chat to me after the talk. So in the example halo, you can see that beyond the virial radius, which is the green line here, you can see that our dynamical estimate seems to sort of start disagreeing with the bin estimates. This doesn't happen for all halos. We have some halos where it keeps agreeing even beyond the virial radius, even 2 or 3 times the virial radius. And whether our dynamical estimates keeps agreeing or not with the bend estimates depends entirely on the types of substructures you have in the outskirts of your halo. So when you have large substructures in your outskirts, those will kind of create a spike density excess some in the outskirts of your halo, and your density, your dynamical density profile will kind of try to smooth that out because the particles are now spread across the orbits. So you will see some divergences here. And it's super interesting how this will affect the profile further in. So this is kind of all I had to say. I'm going to leave you here with a summary of the main points, but the takeaway message is that it seems to be that our dynamical estimates are improving the binned version of the density profiles. And thank you so much for listening.